So those numbers are, okay. All right, we're now being recorded. So if you want to make nasty comments, now's your chance. Yeah, right. Okay. So the first thing I want to do is look at the gravity tide here, calculate the amplitude of it, right? And the way to do that is to look at the potential. We need more board space. The director's got to get on that.
I know. More boards.
Okay. And so that's the potential that that is felt at the location R. And I'm going to pick R to be basically the center of the Earth, and then the top and bottom of this little diagram here. Okay. And I'm going to calculate the difference between the potential here and there, expand out in a Taylor series. That'll give me the tidal force that's acting on the, in this case, the oceans. Okay. And what's going to happen, of course, is since everybody's going around in the orbit around the center of mass of the Earth-Moon system, what I care about is the difference between this potential or force and this potential force on this side, and that's going to lead to this bulge. Okay, and that's also, of course, why you get 2 high tides in a day, not just 1. Okay, so I'm going to Taylor series expand this. Okay. And I'm going to run into collisions already here, but that's all right. I'll go down 1. I'll call this delta R. And then minus okay. All right, so that's the potential at some point delta R away from the center of the planet. And that's, of course, basically is just going to be the radius of the Earth. This term is a constant, so it doesn't do anything. When you're calculating forces, you take a gradient. This term is the one that makes the Earth go around the center of mass of the 2 bodies. And that term tells you the difference between what this part is feeling and that part is feeling in the center. Okay, so that's the tidal potential that we're interested in. All right, just from this, you can roughly estimate. Okay. The height of the tide, this HG I called it. I'm going to just move it over a little farther. Basically, just from dimensional analysis, I'm going to claim that it's the height of the tide divided by the radius of the Earth is going to equal to this tidal potential. Let's see, I'll just call it phi tidal, divided by the potential at the surface of the Earth from its own self-gravity. Okay, so I'll write that one out. That's just G, the mass of the Earth, divided by the radius of the Earth.
So if you're going to take the tidal portion of that total potential, so that's
like sorry, that's supposed to be tidal. Yeah, basically this part here. That's a T. Okay, that ratio.
Question?
Yeah.
Got a question.
How much does, I never knew, how much does the lithosphere respond to the external tidal force compared with water?
Yes, okay. There is a solid body tide. So in about a minute and a half, I'll show you this comes out to be about 35 centimeters, which for the equilibrium tide. That's the ocean. There is a solid body tide, which is about 10 centimeters actually. And it's not just the lithosphere, it's the whole solid body, of course. So the lithosphere does go up and down. Well, we all go up and down twice a day about, 10, 12 centimeters. Well, a little more than that, 15 centimeters. So yeah, there is a solid body tide as well. Now, it turns out that basically over the evolution of most of the Earth's history, the solid body tide really doesn't do anything. And the reason for that is because basically there's so much dissipation in the ocean compared to what you see in the rocks. We think the tidal Q, the best we can estimate it, is it's about 100. So in other words, 1% of the energy that's stored in the solid body tide is dissipated every tidal period, every 12 hours. But in the ocean, it's 10%. Okay, the tidal Q in the ocean is about 11.5. Okay, so that's a factor of 10 difference. And so the solid body tide is a little bit smaller, not a lot, like I just said, about a factor of 3. But the tidal Qs are different by about a factor of 10. So that's a total of about a factor of 30 difference. And we don't care about 3%. Okay? Okay, so this just becomes the mass of the moon over the mass of the Earth times the ratio of the radius of the Earth to AL to the 3rd power. My board management skills have obviously gone to hell in the last year and a half.
The subject of our seminar is our future Blackboard talk is board management.
Okay. All right, so this is about 1 over 80, and that's quite a small number cubed. Okay, so this height isn't very big. So if you actually just plug in the numbers, and I'll just write them out. Okay, you get the gravitational tide from the moon is about 35 centimeters. So you can plug in those numbers and you should get that same result. Okay, so that's the equilibrium tide of the Earth, which if you've ever been to the beach isn't nuts. Usually it's more like a meter in the Pacific, depending on where you are. If you're in certain places in Nova Scotia, it's more like 30 feet or something, but that's a little different. But it's not a bad order of magnitude estimate. And as I said, the solid body tide's about 6, I was remembering the inches, 6 inches, so multiply by 2.5. Okay, to get it in centimeters. Okay, good. So that's the height of the tide. You can estimate then the mass in the tidal bulge here. So in my crappy diagram here, this mass here, and if you want to, you can include the other side. That I'm just going to call the tidal mass. Okay, and I want to estimate that. So the easy way to do that is, we know the height of the tide. The tide's made out of water, so we know its density. We know that the area of the Earth is pi r squared, or 4 pi r squared. Now, of course, the bulge doesn't cover the whole Earth. It covers, I'm going to just say a quarter of it, okay? So I'm going to say that the tidal mass, can people see down at the bottom of the board? Is that okay? Yeah. I'm going to say it's 1/4 of 4 pi times the radius squared times the height of the tide times rho of water, which is convenient because that's 1, right? So if you plug that in, you get sort of 6 times 10 to the 19 grams. Okay? So that's the mass in the bulge. So the next question we got to ask is, okay, fine, what's the torque that is exerted on the Earth by the moon by pulling on that bulge there? Okay, well, the way I've drawn the bulge, it's going to be 0 because it's symmetric around the line joining the centers. Okay, and that's true if you're talking about an equilibrium tide. If the moon and the Earth aren't rotating around each other and the Earth's not spinning, that would be the height of the tide. Of course, they are rotating around each other. And in addition, the Earth is rotating around its own axis. Okay. The fact that the moon is moving, we're going to neglect completely because it's, right, the length of the month is 29 days and the length of the day is 1 day. Okay. So we're going to ignore the 1 over 29. But the fact that the Earth's spinning means that tidal bulge, if there's any friction in the oceans at all, right, we're driving a harmonic oscillator, the oceans, and there's some damping involved. So we've got a damp-driven harmonic oscillator. If there's any friction, we expect there to be a time lag in the response, which there is. It's hard to measure. But that lag, because the Earth, the way I've drawn it here, I'm looking down from the North Pole. I'm imagining it's spinning around this direction, this one too, okay? That tidal bulge is going to get carried forward because the Earth is spinning around so rapidly. Okay, that's a time lag, but it's a forward lag. And there's actually an angle through here. I'll just draw, there's the center. This angle here, which I'm going to call epsilon, is the angle between the actual height of the high tide and the line between the center of the Earth and the moon. Okay. Now, if you're going to try to calculate this, you have to try to figure out what's the friction that's involved. Where's the energy being damped? Okay. And people have been trying to figure that out ever since Immanuel Kant, essentially.
Do we have guesses? Do we have audience guesses?
Yes. Okay, good.
Okay. Best guesses for where the friction is.
Well,
So at the water lithosphere boundary.
at the shore.
At the shore.
Yeah. It's not quite at the shore. Turns out most of it, 2/3 of it, is in shallow continental shelves, essentially. A lot of it in the Bering Sea, actually, along the Aleutians. There's some small amount of it up in Newfoundland, in the Bay of Fundy, and in the Irish Sea. So just generally around the Earth in shallow continental shelves is where you get the most. But 1/3 of it actually is coming off of the Mid-Atlantic Ridge and off the Hawaiian chain in the middle of the Pacific at the bottom of the ocean. And that's a cute story, which I really like. I'll waste some time telling you just because it's fun. So you have these tides going back and forth, right? And when they run into a mountain range, of course, the water has to go up. And that line gets up to the surface and it breaks. And that accounts for about 30% of the dissipation. What's that? Okay, I thought I heard a question. The other 2/3 is though in the continental shelves. And this has actually been measured now by looking at wave patterns on the surface of the ocean using satellite techniques. So we actually can measure the amount of energy being dissipated. And that does agree with this estimate that I gave you earlier that Q is about 11 or so.
So to have that gravity wave, it has to be stably stratified. Yeah?
The ocean, yes, it is. Yeah. This was actually discovered by the US Navy. They didn't know what they were looking at. They were shooting sonar beams, very high intensity ones. You can imagine why. And they diffract off of these gravity waves. And so they figured out there were gravity waves in the middle of the damn Pacific, and they came and went, every 12 hours, depending which way they were shooting their sonars off. So yeah, that's another way to detect them. But that wasn't known to geophysicists for some time. So yeah, you could have done it that way too. Now this was
actually coming from these structures in the
on the bottom of the ocean. Yeah, that's right. Yeah, seamounts basically. Yeah. Now they're also analytic. Well, I shouldn't say that. They were
mountains, or is it
No, it's off of a chain of mountains, so mountain range.
okay.
Yeah. If you look at the Hawaiian Islands, they sort of go back. If you look underneath the ocean, they go all the way up almost to the Aleutians. So the claim is that the plate's been rotating and moving, and there's a thermal plume that's been sitting there producing islands all along. And so that's enough to launch these gravity waves. Yeah. And the other way to do it is that, as I say, at a mid-ocean ridge, which is a different thing. That's where two plates where you have an upwelling that's going apart, and you have mid-ocean ridges that are spreading zones. But they launch gravity waves too. Yeah. Okay. All right, so the torque. I'm not going to try to estimate that number. As I say, this was done by people looking at the areas of these continental shelves back in the turn of the last century. And then Jeffries was the one who really sort of got it right. And basically, they assumed that you were generating turbulence off the bottom of the ocean floor. If you calculate the molecular viscosity, it doesn't produce any dissipation at all. Another question.
What did Kant think?
He didn't know. Had no idea. Yeah. But well, he realized. So people had realized. Newton explained the semi-diurnal tide, and then astronomers were looking at the moon, and they realized, over decades, that the moon was not where it should be over a long period of time, and it was seen to be, and that mismatch was increasing with time. And what was happening is that, of course, the tides were removing angular momentum from the Earth, which changed the spin period of the Earth, and they put the angular momentum in the moon, so they changed the semi-major axis. Both those things will change where the moon ends up at a given, solar day-based time. And the astronomers realized that was going on, and Kant realized that the moon was probably being influenced by the tides, but didn't know why the bulge didn't line up. Okay. Anyway, you can do an order of magnitude estimate of that, but I'm not going to go through that. I'm going to give you an order of magnitude estimate of the thermal tide. Okay. But let me just write down what the torque is. Now I got to erase something. All right. People got the numbers, right? They're all memorized. I'm going to add, there's a quiz at the end. Okay, we don't need that anymore either. Okay. All right, so the torque, the lunar torque, lunar gravitational tidal torque. People should remember this one. Okay. All right, now the R here is the radius of the Earth, right? Because we're talking about an R out to here, or actually to the location of the bulge here. Okay. Now the force, so this is the regular force. That's to account for the fact that you're worried about the tidal part of it. And then you need the mass of the tide, sorry, the tidal bulge. And then you need, right, this is a cross product, so there must be some sign of some angle here. It turns out to be 2 epsilon. Okay. So that's the expression for the tidal torque, okay? And I've written down here what that MT is, okay? And this is the, right, it's the gravity from the moon is pulling on this tidal bulge. So that's why it's the mass of the moon divided by the separation between the Earth and the moon, okay? This, as I said, that radius comes from that R, okay? Now this MT, I didn't write it down, but you can actually see here. Suppose you do this, you can write this as, well, I'm gonna cancel off the, right, this is R Earth squared. And then I'm going to actually multiply by R to the Earth again and write this as H over R Earth. And then I'm going to write this is rho Earth and rho water over rho Earth. Okay, and this is pi R cubed now times the density of the Earth. So that's the mass of the Earth, right? But this H here, that H over R Earth, that's got a ratio of mass of the moon to the mass of the Earth. All right. So this thing gets turned back into a mass of the moon again. So you end up getting 2 powers of the mass of the moon here, which is maybe if you've looked at this tidal theory before, you remember it was like G times the mass of the perturbing body squared. So that's where that comes in. Okay. I'm not going to write that out. I'm just going to write out what the value of it is. Okay, so that's a torque. It's a dyne centimeter, right? Okay, so that's a number to sort of keep in mind. It's around 10 to the 23, well, almost 10 to the 24 dyne centimeter. Okay, so one of the interesting things about that is then you can calculate, well, like what's the typical time scale involved from this tidal behavior? Well, to do that, I'm going to say, well, we know that the angular momentum of the Earth changes with time as a result of this torque, like that, right? That's what a torque is. It's a rate of change of an angular momentum. So the time scale for the gravitational tide is going to be, okay? And remember, this thing up here was I of the Earth, omega of the Earth over TL. Remember, the omega of the Earth is just 2 pi over 24 hours. I'll just call that the LOD. And that's about, I wrote this down for myself, I think. Thought I did. Yeah. Okay. All right. So if you plug in that, which I wrote down the expression for earlier, L of the Earth, the angular momentum of the Earth, the spin angular momentum, I maybe should have called that S, is, hang on. Okay. So if you use that and use our expression there for the tide, the tidal torque, this comes out to be about 4 gigayears. Okay. So that's the tidal time scale associated with the moon, which seems like okay, we think the Earth-Moon system's that old. Unfortunately, if you actually take this number and then integrate backwards using the tidal equations, of course, right, this height of the tide varies rapidly with the distance between the Earth and the moon. In fact, that time scale varies even more rapidly than that, as you can work out. So if you just integrate it backwards, the moon hits the Earth about 1.5 or 2 billion years ago. Okay, and that we know is wrong because we actually have moon rocks which have been dated to 4.4 billion years. Earth rocks are not that old, at least none of them that we've ever found. You can find zircons that are that old, close to that old. Zircons are a little, they're not crystals, they're sort of like bits of glass that are extremely old. They're in rocks that are a lot younger than the zircons are because they're hard to get rid of. And they go back to, my recollection is just over 4 billion years. The oldest rocks are like 3.8 billion years old. And that's because of plate tectonics, basically. That and our inability to find things, probably. There's probably some older stuff around. Okay, good. I better get moving because it's already 3:37. I haven't said anything about thermal tides yet. All right. So let me erase all of this except that one picture there. Now, the reason, of course, that the moon didn't run into the Earth in the past almost certainly has to do with the fact that the dissipation rate in the oceans, that varies with the shapes and the sizes of the oceans. And in the past, the Earth was spinning faster. And the other thing about the tidal dissipation rate is it does depend on the frequency that you're driving the oceans at, okay? So in fact, the Q in the past was noticeably larger, we think, than it is now by factors of several. And that's enough to extend the length of the lifetime back to 4.5 billion years. All right, thermal tides. Okay, I'm going to use that same formula, so I shouldn't have erased it. Okay. Typical. Right. The thermal tidal torque, it's going to be the same R cross F, but now thermal. Okay. And that R is still going to be the Earth's radius, right? Because I'm talking about this bulge here, which is sitting at the Earth's radius. Okay. And the force is going to look quite a bit different, but not all that different. Right? It's that same. And I'll write the sign of the angle later. You know, there's the G and the M over the separation squared. That's the force of gravity. But now the M and the A are different, right? The M now is solar because it's the gravity from the sun. And this is the semi-major axis of the Earth's orbit, right? So now I'm talking about this pulling on that. Okay, but it's the same formula, just with different interpretation. And then I need the mass of the thermal tide, which I call TH, and then the sine of that angle, which, in fact, I'm going to draw it right now. It actually, the bulge looks like this. I need another color. Hopefully red will come out. It's about like this. Again, exaggerated, but this angle here, this is basically, it's at 10:30 in the morning. okay, and 10:30 at night. Of course, that's 6 in the morning. That's 12 noon right there. So this is what is that? 6 and 3. It's 4.5 hours. So it's pretty late. It's a big angle, right? Corresponds to like 60 degrees, I think, or whatever it is, 59. Okay. So that's one big difference. Here, the angle is very small, a few degrees. And there it's basically 45 degrees, if you like. Okay, so that boosts this effect of this tide up by quite a bit. Okay. All right, so how do you figure out the mass of this thermal tide? Well, I'm going to, again, use that same formula, right? I'm going to say it's 1/4 of 4 pi r Earth squared times the height of the thermal tide times the density of air. Okay, it's the same expression for the mass of the bulge. So now what we have to do is we have to work, this we know, it's about, water was 1, I said, the air is like 10 to the minus 3 is the density. What's the height of the thermal tide? Okay, so that's what I'm going to calculate next. Okay, now I'm actually going to do it in terms of the pressure rather than this height. And to do that, I'm going to say, okay, we're talking about the Earth's atmosphere. It is in hydrostatic equilibrium very nearly. It's a very good approximation. Okay. And so I'm going to write down the equations of motion, right? The energy equation for air. Yeah.
The large angle, you want to think about it in analogy to the other one.
Yes.
And so what then is the corresponding dissipation that causes it? Is it, because now, I mean, is it actually that the surface is more, has just more structure?
Well, it's driven differently.
Okay.
It's driven thermally.
Right.
So when the moon is up here, you get a bulge here.
Yeah.
Okay. When the sun's here, I said the natural equilibrium type is to have a bulge this way.
But then is it the actual surface? Like the
It does depend on the thermal properties.
of the atmosphere?
It does depend on the specific heat of the atmosphere. It really depends on the heating and cooling rates. Okay.
Okay.
Which I'll quickly go through very quickly. Yeah, very quickly. Why it's a big angle. Why it's not either here or here. It's in between. Now it also, of course, depends. Again, remember this is a damp-driven harmonic oscillator. I'll derive the equation in a second. And so the angle here depends on the difference between the rate at which you're driving the harmonic oscillator and the rate at which it would naturally ring at. Okay. And it turns out those two numbers are close to each other. Okay. And that's not a coincidence, is my claim. A has 24 hours. Okay. Because it was pushed to be at that resonance. And so, you know, if it was exactly at resonance, of course, the thing would have a 0 lag. And if the day were shorter than the thermal period, then the lag would be the other way around. The bulge would go this way. Okay. Now the way I've drawn the bulge, right? The sun is now trying to pull this bulge harder than it's able to pull that one. So it's trying to accelerate the thing in the same direction the Earth's spinning. So this bulge shortens the length of day, whereas that bulge increases the length of day. Now, on the other hand, if you make the length of day less than that thermal period, which I'll explain in a second, then it'll do the opposite. It'll try to spin down the Earth the same way this one does. And that was true for most of the Earth's history, I claim. That it was actually acting in the same sense as the lunar tide was. Okay, so what is that period roughly, right? I mean, it's order of magnitude. The thermal period is going to be something like 2 pi times the radius of the Earth, because it's going around the equator, right? Divided by, well, it's moving at roughly the sound speed, CS. Okay. And I'll just put in here, now I'm going to write another T. By this, I mean the temperature of the Earth's atmosphere. And that's important because, as it turns out in the past, like I said, I claim from looking at data that temperature, the mean temperature of the Earth back 1 billion years ago, 1.5 billion years ago, was about 50 degrees Celsius. That's the mean temperature of the whole planet. It would have been kind of unpleasant, I think, for us. Now, it's not quite that. There's some sort of eigenvalue that goes in there, but it's roughly that. Okay. And if you just do it without the beta in there, I think you get about 30 hours. And the one that we think it is correct today is about 22.8 hours, somewhere in that range.
When you say thermal period, you mean acoustical or dynamic?
It's acoustical. Yeah, it's acoustic period. It's basically a sound wave, what you're driving. It's called a Lamb wave, because geophysicists, this guy Horace Lamb, worked this out. But it's basically a sound wave. Yeah. It's a global wave, though, right? The period is a quarter. Sorry, it's a half of the Earth's circumference, right? So it's a long scale wave, and it's also, I should say, it goes quite high in the atmosphere. It goes way up above, about 100 kilometers up. Okay. And that sets that parameter, which I'm not going to go into. Okay. All right. So now, how am I going to estimate this H? Well, first of all, the way this thing was discovered, more or less, well, certainly was nailed down, is you see pressure perturbations on the surface of the Earth if you're down in the tropics. Anybody with a barometer can see this. They were seen in the 1800s, even the 1700s. The barometer just goes like this, up and down twice a day. Okay, and it varies by about a millimeter of mercury, or a millibar. Okay, and the period, as I said, is 12 hours. And it's just as I said here, right? The peak pressure is at 10:30 in the morning, and then the minimum is at whatever is that 4:30 in the afternoon. Okay. Now, of course, it's also right. When's the temperature highest? Temperature's not highest at noon. It's at
That's why our coffee and tea hours are always at 10:30 and 4:30.
It's like the pressure variations. Exactly. Exactly. Okay. All right. So I want to convert this into a pressure just because it's more convenient. And I'm going to use this fact that the Earth's atmosphere is in hydrostatic equilibrium, right? dPdr is equal to rho g. Okay. And I'm just gonna, we're doing perturbation theory, right? So we're gonna eventually say that P equals, P0 plus P1, and et cetera, right? But for now, I'm just gonna ignore all that. This is order of magnitude, not freshman physics. Okay, so this basically says that if you've got this thermal tide here, which is height HTH, right? Then I'm going to call it actually P2, not P1, because it's a semi-diurnal tide. So is it Legendre, Laguerre? Whose polynomial is it? P2. Legendre. Yeah. Okay. Good. That's what I'm drawing here, right? Okay. So this says that P2 over H thermal is equal to rho 0 G, okay? Or H thermal times rho is equal to P2 over G, okay? And that's what I'm going to plug in here. Okay, so this is all right. All right, so now what I need to do is I need to calculate what is the pressure perturbation down on the ground. Well, you can cheat because you already know the answer. It's a millimeter of mercury, it's a millibar. Okay, that's the easy way to do it. And if you do that, you get that this mass, don't you believe in pure theory, right? It's a critique of pure reason.
You know how I feel about that.
Yes, I know how you feel about that. That's why I'm teasing you. Okay. I wrote it down. What did I do with it? It's a little smaller than the tide. Go back. Now I've lost it. It's about 10 to the 18th. Okay. So that's about a factor of 10-ish, less than what I wrote down for the other one. right? The thermal tide, I mean, the gravitational tide, I got 10 to the 19. All right. On the other hand, right, that's a pretty big number too, right? So it turns out though, if you calculate the torque, I'm supposed to write down sine of, what do I call that thing? I'll just call it theta. I'll call it psi. That, you know, this is of order unity. So that's a little bigger. This is smaller. When you get done with all of this, this torque is about today 1/10 or 1/15 of the lunar torque. Okay. All right. Now you can actually calculate this order of magnitude, but I've only got 10 more minutes. I don't think it's worth going through that in great detail. Okay, I want to talk a little bit about the results of this. Okay, basically you write down the, you know, what is it? The first law of thermodynamics. You know, dE equals TdS minus PdV, right? And you just go from there, and you get pretty straightforward what the energy equation is. But you're driving the energy equation, right? Because the sun is putting heat into your air. And of course, the air is also radiating back out into space. And those two are in equilibrium, except currently we've sort of screwed that up by putting more opacity in the atmosphere. So we're actually accumulating heat in the atmosphere. Okay. But basically they're in equilibrium. But of course, you know, you've noticed probably that it's hotter in the daytime and colder at night, right? You're dumping in heat in the daytime and you're radiating it all the time. And so when the sun goes down, you start radiating heat away, it gets cold. So that produces a time variation in the rate of input of net rate of input of heat into the atmosphere. Okay.
I wanted to see something on the Canadian Tire website before you go.
What's that?
Yeah, I've been shopping on Canadian Tire and trying to get all kinds of stuff we need, including now I'm looking at power bars. But look at the stuff I have already.
Thinking.
You want to mute yourself?
I don't think it was him.
It wasn't him. Okay.
But I had a question though. If you actually just do these barometric measurements, have people noticed changes in them over time as the heat has gone up?
So far, not.
Okay.
These were the people that noticed this were basically British people in. Because they were recording everything, and people sort of gave up in the last century recording these things.
It could be an interesting alternate way to measure the heat.
Well, adding CO2 to the atmosphere will change the response of the atmosphere to the heating from the sun.
Right.
We've seen that in our global circulation model, so you could try to do that, yes.
Yeah, that'd be
Yeah.
like easy, right? Just take a vote, do the barometric measurement.
Yep. Yeah. Okay.
It's a good field project for you guys.
Okay, let me just quickly write down the equation of motion. This won't surprise you, right? We're talking about sound waves. If you do go through the algebra and use pressure variation as your variable, because that's the one that's easy to measure, as we're just describing. This P2 okay, that looks like a sound wave, right? This gamma I just put in by hand is having to do with some sort of way of removing energy from these waves, okay? It's not friction on the ground, as it turns out, but it's called a friction. And then if you just go through the algebra, you get Boltzmann's constant, mu, CV. So this is just a pure number, right? This is 3/2 for air, basically, times rho 0, the density of the atmosphere, times gamma times Q dot. Q, remember, is TdS, right? So the rate of change of the pressure perturbation is just proportional to the rate of change, well, the second derivative essentially of the rate of putting energy into the atmosphere. And remember, that's the net change, right? Okay. All right. And then you can relate this Q dot, right? I started off writing, you know, TdS, dE, and, you know, energy per gram. normally what we think about coming from the sun is the energy per square centimeter, not per gram. So it's easy to convert from those, from one to the other, right? It's just the flux divided by the mass per unit area, or the column. Okay. And then using hydrostatic equilibrium, that's just okay. And this, you know, right? It's 1,360 watts per square meter. Okay. But we're interested in averaged over the surface of the Earth, so it's 1/4 of that. So it's about 340 watts per square meter. But normally I think of that as coming right through the atmosphere and not doing anything. Okay. Well, it turns out about half of it gets absorbed by the atmosphere, either on the way in or on the way out. But the dominant contribution to that flux heating the atmosphere is actually not radiation directly. On the way in, it gets maybe about 20%. Then there's the radiation coming from the ground. That's thermal radiation. About 5% or so of that gets absorbed in the atmosphere. That's the CO2. The bulk of it is latent heat of vaporization of water. Right? The sun shines on the water down in the tropics. If you've ever been down there, it rains all the time. That water goes up as a vapor. When it gets high enough, it condenses, it makes little droplets, and that releases the latent heat. And that's what heats the atmosphere. That's the bulk of it. Just not the first thing I would have thought of, but that's the way it works. Okay. All right. So then, I mean, just from this, right, you can estimate what P2 is. P2, there's two frequencies here, and it's going to be proportional to this Q dot or to F. Okay. Now we're interested in the part that is driving this double humped thing. So it's a semi-diurnal. We want to pick out the one that has a 12-hour period. So you got to do a Fourier transform of the sun. Remember the sun, the amount of sun that you get per time looks like this is dead zero, then it goes up and it comes back down. And this is like 6 a.m. and this is 6 p.m. We're in the tropics, remember, right? The sun actually does that. Okay. So you got to do the Fourier transform of that. So then the estimate is pretty straightforward. You just go P2 is roughly, there's this 3/2 pi. That's from the Fourier transform. Then there's this KB over mu CB. There's a rho 0 G over P0 times F. And then there's this funny function of frequency. Okay, and you can just see where I'm getting this, right? That's the rho 0. There's a KB over this. The Q dot, I'm plugging in here, getting GF over P0. And then this, you got to work through with the derivatives of QR. Okay. Well, not surprisingly, right? This is a damped driven harmonic oscillator. It's linear. Remember, this thing is 1 millibar out of 1 bar. So it's part in 1,000. That's linear. So this is, you're going to get the usual. I'll just draw that function, right? So this is, you know, period of the length of day, which is basically, you know, 2 pi over the spin period of the Earth. That thing there I'm going to call as this resonant period, P thermal. And then what I'm plotting here is the torque, this thermal torque. And it's going to look like this. Right, the usual, that's the torque response. The pressure would just be a single peak thing, but the torque, because this angle shifts as you go through the resonance, that gives you the change in sign. Okay. Now today on that same plot, the lunar torque, which is of the opposite sign, but I'm going to take the absolute value, sits up here, well above that peak. And today we're sitting, this thing's at, we think, 22.8 hours, and we're sitting here a little bit off the peak, but not by much, at 24 hours. Okay. Of course, now in the past, we know the day was shorter. It was over here. And it was, the torque was of the opposite sign, as I said. And then as the moon kept pulling angular momentum out, this torque also pulled angular momentum out of the spin of the Earth. And so we were just moving this way as time goes on. And then about 2.5 billion years ago, we went through this resonance. Now, my claim is that in the past, I already told you that this lunar torque can't stay at this value in the past. It has actually, you would have thought it got bigger, but it had to be smaller. So the claim is that it was actually like this, comparable to the height of that peak. Okay, but remember now, these two at that point, they're pushing in opposite directions. The moon's still trying to slow the spin of the Earth, but this torque's now trying to speed it up. And you can get into a balance right there at roughly that resonant period. And what that means is there's a torque trying to spin up the Earth, there's a torque trying to spin it down, they equal each other. That means the length of the day stays fixed. Okay. In the meantime, this lunar torque is still trying to push the moon away, and it does. So the moon is going to keep moving away. Okay. Which nominally will reduce its torque even more. Okay. But we're not in that state today. So somehow it got out of the state. But while it was in that state, the length of day was fixed. And I dug around through a lot of literature. And the data isn't great, but there are tidal deposits in sandstones. I've got a rock up my office. It's 3.2 billion years old. It's from the Barberton Greenstone in South Africa. And there are tidal deposits in that geologic region, which show you that they just basically count the number of days per month, okay? And that's at 3.2 billion years ago. And I can see similar data all the way down to the present. And the length of day was roughly fixed. The number of days per month does what you'd think it'd do if the angular momentum were conserved. It would go up to begin with and then come down as you reach the present. But it takes a jaunt in between there from about 2.5 billion years ago to about 1.5 billion years ago. Okay, and that's because this torque became comparable to the lunar torque, and it dumped a lot of angular momentum into the Earth-Moon system, and it pulled it out of the Earth's orbit around the sun. Okay, so it broke out of that about 1 billion years ago, and I think it's because the composition of the atmosphere changed. There had to have been a lot of CO2 back at the time. That's been known for a long time because that's what's called the faint young sun problem. We know that there were liquid oceans over basically the entire time that I've been talking about, 3.2 billion years ago to now. These are tidal deposits in an ocean or a big body of water. So that means there's a big liquid body of water on the planet 3.2 billion years ago when the sun was about 20% less luminous. And if the atmosphere were like today, the whole thing would have been frozen solid. Okay, so you knew it was warmer, and that's probably because of CO2 in the atmosphere. But that also affects the height of this peak here. It affects the thermal tide. Okay, now there's one other thing you can get out of this. Like I say, today the period is 22.8 hours. When it was locked 1 billion years ago, the length of day was 19.5 hours. Okay, and that period, as I said, well, it's pretty clear the radius of the Earth has not changed over that time. But that temperature did change, I claim. And as I say, if you put it to about 50 degrees, the global circulation models that we're running tell you that the period then was around 19.5 hours. So now we have a way to measure the temperature of the Earth over about 1 billion years, or a little more than that, of the Earth's history, back 1.5 to 2 billion years ago. Okay, and it also tests your global circulation models. To do this, you got to have about 1/10 of a bar of CO2 in the atmosphere. Right, today we have 1/10 of a millibar, although we're doing our best to get it up to a millibar. Go. All right. Okay, and the temperature that it predicts is, like I say, it's around 50 degrees Celsius back at the time, which gives you a period which corresponds to that 19 hours. So that looks like a pretty consistent story, and it's a way to test if we get better geologic data, like more of these tidal deposits, or there's another technique which I haven't mentioned for figuring out the spin period of the Earth as well as the length of the month or the semi-major axis of the moon. And that'll allow you to constrain the temperature history of the Earth over about 1 billion years, you know, starting about 2.5 billion years ago, going to about 1 billion. And that's a good normalization for our global circulation models. It's a good way to check whether they're behaving under conditions that are different than they are today. So that's why the day is 24 hours long, because this resonant period back then when we were trapped in it was about 19 hours. The Earth escaped from that about 1 billion years ago, and it's gradually been getting longer, but we're still pretty close to the resonance, right? The length of day today is 24 hours, and the resonant period has followed us up because the temperature's been decreasing, okay, along with the CO2.
If we really try hard and get that temperature up, as want to do, are we gonna go back into 22.8? Because I'm just wondering, like,
You'll go-
these flips and
This-
like,
This solid curve here, as you're seeing, will in fact move to shorter periods. That's right. Okay. So we could get,
we need a longer day, not a shorter day. We have longer day.
yeah, well, then you got to lower the, got to start pulling carbon dioxide out of the air.
Exactly.